second speaker of the day. We have Alec Ardwal from Microsoft Research. He's going to be talking about reinforcement learning with rich observations.
Thank you. Let me start by thanking the organizers. It's always good to have an excuse to visit Berkeley again. So today I'll be talking about some recent work we've been doing in reinforcement learning, this joint work with Nan from Michigan, who was a summer intern, Akshay, who I think is in the back, and colleagues John and Rob from Microsoft Research. Probably most people in the room know what reinforcement learning is, but I just want to highlight a couple of salient aspects still just to sort of set the ground. So a pretty prototypical picture of reinforcement learning is we have an agent that's acting in the world, hopefully purposefully. It's a sequential decision-making problem. The agent perceives its current state of the world, which in this case might just be the rat sort of looking around to see where it is, takes an action, modifies its location in this example, for instance, and repeats this process a few times. In this process, it picks up some reward, and its goal is to sort of maximize the net reward that's picking up. For instance, the reward might actually just be 0 for the most part here until the rat reaches a piece of cheese, and then it might be 1 or 0 depending on whether the rat likes the cheese or not. Right now, the two salient properties here that we want to think about and keep in mind is, so one, unlike a lot of other machine learning problems, actions have consequences here, right? So when the rat moves to a new location, that defines what effect its next action is going to have, right? So your actions modify your state, which means they influence what rewards you might be able to pick up in the future. And B, this really is, there is a long-term aspect here. So it's not like you take an action, you make a prediction, you get a label. Yes, you might get some reward, but for instance, in this example, the reward is 0 at most time steps until the very end. So you really are reasoning over sequences of decisions.
Alec?
Yes?
This is not a very typical example, the rat and the for reinforcement. Is there a reason you chose the one with no probabilities and so on like this? Yeah,
so I chose, in particular, the one thing I wanted to really highlight was that there is no intermediate reward at all, right? So I really want to kind of reinforce the aspect that you get reward at the end. And then the other thing which I'll kind of, which I like about this very simple example, which I'll sort of toggle back and forth between, as you can, like mazes are nice because you can think about the maze either in terms of like a discrete grid that you're located on, or in terms of your actual perception of the grid through visual cues. And we'll see how they, which way you're thinking about the problem kind of influences how you design solutions and so on. But you're right that everything we'll talk about will involve sort of a stochastic world with probabilities and yes, absolutely. We definitely do not want, I mean, depending on like how finely you think about even this very simple problem, like the rat moving forward doesn't always mean that it moves forward by the same amount and so on. So there is stochasticity even in this very simple example. Right, so there's probably everybody in the room has perceived there's a lot of excitement, especially coming from the empirical side, about reinforcement learning these days. A lot of the driver has been this kind sort of results coming out about how to synthesize deep learning and reinforcement learning in interesting ways, in particular in game playing type domains. And let's kind of try to map it back to this, again, this very simple example that we just saw. So remember, when the rat starts out, it knows nothing about the world. It doesn't even know that a piece of cheese exists. It's just sort of moving around randomly. And maybe after a lot of time of acting in this space, it finally stumbles upon the piece of the cheese, and it has learned that, oh, there was actually something kind of interesting to be had here. But before you see the piece of cheese for the first time, this was, there is sort of a huge exploration problem here, right? Which is, you have no information, and you have to act in order to acquire this information. Now, one thing that's kind of dissatisfactory about the way a lot of the empirical approaches have been going so far is, while they're using a lot of interesting things on the machine learning on the modeling side, the exploration is often pretty simplistic. Often you're just doing basically uniformly random exploration with some small probability, which basically means if you think about what's the chance of you actually stumbling upon the piece of cheese even once, if I make this maze large enough, that's negligibly small. So, so it kind of suggests that just having very powerful reasoning about just having very powerful perceptual abilities about the world might not be sufficient in order to solve the reinforcement learning problem well. On the other side, there's some very nice theory that has been done in reinforcement learning, especially like going back to even late 90s, early 2000s, where people thought pretty deeply about reinforcement learning under a very specific setting of MDPs with small number of states. I'll define a lot of the terms as we go on. But basically, there were very nice algorithms developed that specifically thought about this exploration aspect of the problem, when you could basically think of this maze as a discrete grid with a small number of cells, roughly, just in a very simple, overly simplified sense. Right, and then they were able to show how to solve the exploration problem well and how to learn in a sample efficient manner. However, that's not quite practical, because often you cannot think of the world as having sort of a small number of discrete cells. You really do want to think of a world where you are perceiving some complex observations through various sensory inputs, and you want to think of maybe that as your state. And so there is kind of a mismatch between what we would like to do practically, what the theory is telling us, and the overarching goal of this work is to try and close this gap to the extent possible and provide some theoretical insights into how we can learn near optimal policies for reinforcement learning in a sample efficient manner when we perceive the world through these complex sensory inputs. So that's the high level goal here. With that goal in mind, just a very quick sneak peek of what I'll tell you about. I'll present a single formalism and a single algorithm that will allow us to derive conclusions within a number of reinforcement learning formalisms and models that people have looked at in the literature. So it's going to be something that takes the existing literature, which does solve the small state MDP setting quite well, but also extends it, for instance, to large state MDPs where the number of states are very large, but they exhibit some additional structure. Or maybe even partially observable MDPs, but where you're not necessarily reasoning over very large histories very far in the past. And even more general models like predictive state representations, and in some cases even continuous action spaces and so on. So it's going to be a single way of thinking about many different settings that people have studied in reinforcement learning. Obviously, very general settings are often not the most intuitive one to go about in talks. So I'll, for the most part, focus on MDPs with a large number of states and additional structure. And I'll give you hints about how things generalize as we are going through the material. And the key driver in doing all of this is a new measure for the hardness of exploration, which we call Bellman rank, that I'll introduce. And we'll give an algorithm which has sample complexity that scales with this Bellman rank of a reinforcement learning problem. And I'll show how this sort of translates to interesting consequences in several plausible applications of reinforcement learning. So let's, since kind of everything is going to be generalization and variants of MDPs, let's start by setting up an MDP first. So in an MDP, so this is a sequential process. So you start from some initial state. In fact, you have a distribution over the initial states. I will I'll use x's to denote states. And we're going to think of x's more as sort of the feature vectors that we use in machine learning, right? So we'll think of them as basically being continuous, high dimensional, and not at most 10 in number or anything like that, right? So that's the idea here. So gamma 1 is your initial state distribution. You perceive the state, you take an action, get some instantaneous reward, and the action and your current state induces a distribution over the next state. So this is an MDP, meaning that the process is Markovian, meaning at time, your transition at time h only depends on the current state and the current action. Your reward at the current step only depends on the state and action you're in. So everything is Markovian. Things don't quite need to be Markovian for a lot of our theory to go through, but just again, simplification. We're going to assume that the process is episodic, so I'll not do infinite horizon. We take a sequence of h actions. The process stops. We tally up the total reward we have picked up, and then we can repeat another trajectory of length h. Right? So that's going to be the setting. And our goal is going to be to maximize the total reward we pick up over this h-step sequence. In particular, we're not going to take arbitrary sequences of actions. Really what we want to think about is how do I map states to actions. So really what we'll be after are what are called policies, which are these mappings from x's to a's. And we'll try, the goal will be to try and find a policy pi that picks up a good cumulative reward after 8 steps. Isha?
If you're doing a finite horizon,
yeah,
the optimal policy needs to get not only the state, but also how many steps are left.
Yeah, so I kind of did not call this one out, which is I'm just, for now, I'll assume that I index my states with the level h, so I just augment, I replicate the states by a factor of h, and then otherwise, I mean, I can do everything the way you were suggesting, it just makes for messier notation, right? So I just...
I understand the notation.
Yes. So it's just, let's just think of distinct states at each level, and then I don't need to do this. Okay. Let's just go over some quick examples where things make sense. So now instead of putting a rat in a maze, so this is kind of closer to what people have studied pretty much to death. Right? So this is kind of a grid world setting. You start out somewhere. Your goal is maybe to get somewhere else. You have some actions that move you forward, backward, right, left. Maybe you get a reward of 1 on reaching the target. Maybe you get a reward of -100 if you fall into the lava and die. And so that's kind of the toy view of this setting. What we are interested in is this alternative view, which is maybe closer to a more realistic setting where maybe your agent has a head-mounted camera and this is the first-person perspective of the agent. So we would really like the x's to be these images, and we would like to reason over them, and we'll see how to. It doesn't have to be, of course, about sort of robots and grids and navigation. You can think of a very different setting which maps equally well to the formalism. So you can think of web search. User arrives, they have some intent, they issue a query that's a partial expression of this intent. The search engine takes an action which is to present a result. The user provides some feedback by maybe clicking on things. Then they do a reformulation of their query if they are not quite satisfied, which depends on the previous query and the results you displayed. And this process iterates a few times, and your goal might be to sort of minimize like the length of this interaction, or the user eventually finding a satisfactory result or something. Emma?
This is an interesting one because I feel like it's really like information gathering MDP because the state of the user is only what they're looking for. That's
Yes.
that. And then the observations.
Right.
Just doing information gathering.
Yes, that's true. Okay, so let's briefly review what we know about MDPs. Again, I'm kind of simplifying and glossing over a lot of things here, but at a very high level, what we know is if you give me an MDP that has cardinality of x number of states, A actions, h is, remember, the number of the horizon, the number of steps I take, and epsilon is the accuracy to which I want to learn a policy, then I can do so in using collecting trajectories, number of experiences, that are polynomial in all of these quantities, which is great for the most part except for the dependence on the cardinality of x, right? It basically tells us that If I'm thinking about the world as this grid, then I'm okay. If I'm thinking about the world as perceived through these images, I'm not okay, because the cardinality of x is basically infinite. Now, before we get too kind of harsh about such a result, we should keep in mind that, by the way, some restriction on the number of states is unavoidable for sample efficient learning. So this is, before we even think about any computational or other considerations, this is just statistically kind of unavoidable making some structural assumption on the process, because if you do not, if you think about, you've got basically this branching process, right? You've got sequences of length h. At every step you have a possible action, so you can just construct a giant search tree where everything is distinct, and you have to find sort of the right leaf. If you don't make any structural assumption, that's going to scale basically with the number of leaves in this tree, the sample complexity of doing so, which very quickly induces a omega of a to the h lower bound, right? So we know that we'll have an exponentially worse dependence on horizon if we don't make any structural assumption on the process.
So just to clarify some terminology, so when you say sample and when you say data in this context, so what do you exactly mean?
So right, so a sample for me is a trajectory of length h. So
and then you decide what will be the next thing in that trajectory, or?
So yes, so this is kind of the on policy setting for reinforcement learning, which is I get to choose the policy which I act according to every time. The off policy setting is significantly harder.
You don't get to choose the states, right? You get to choose the actions.
I get to, yeah, I pick the policy that I'll be using at a particular trajectory. Yes. Okay. So now again, there is kind of a very simple criticism of the simple lower bound, which is obviously I should not think of all the states as distinct, because naturally in real life problems, if I'm standing here, I move one step to the right, then what I perceive doesn't really change by that much. So somehow, my states share a lot of characteristics. I should transfer information across them. I should basically generalize. Right? That's what machine learning is all about. And people have actually thought a fair bit about how to generalize in reinforcement learning settings. One of the predominant paradigms for doing this is what's called a value function approximation. So I'll quickly recap some of the important basics from the function approximation literature before we go into our work. Okay. So the basic object of interest that you start with for value function approximation is what's called the Q star function, which is basically a solution to the problem, right? So what Q star tells you is that if you give a state x and a candidate action A, then what is the best possible reward you can pick up if you take action A in x and then act optimally thereafter in the rest of the future, right? So a good example to think about is if you're solving shortest path problem, right? Then let's say your state is just your current node in the graph, and an action might be to jump to one of the other nodes, and then you're asking, okay, what's the shortest distance from here to my target node? And that's basically what Q star will tell you. So Q star is basically solving your problem for you, because it just sort of removes all the long-term planning aspect of the problem, right? If you know what's the best reward you can pick up from every action, then you just take the action from which you can pick up the best reward in the future, right? So there is a very simple thing to do. If somebody gives you the Q star function, you just act greedy according to it, and that describes an optimal policy. So since the Q star function is so powerful, so useful, maybe you should try to approximate this function. Well, we know a thing or two about doing approximating functions, right? So let's just take a big class of candidate Q star functions. Maybe I'll parameterize this linearly, or with neural networks, or with decision trees, whatever your favorite function class is. And I'll try to, all these functions will have same structure as Q star, so they'll map XA pairs to real numbers. And then I'll search over this entire class, and I will try to find one that's close to Q star. And for simplicity, I'll actually also grant you that Q star lies in this class for now. So your search problem is actually extremely kind of nice. You're trying to find this function q star. You know one of the functions in the class is q star. You just have to find it. And just like q star has sort of describes this optimal policy in a greedy fashion, you can think of, in fact, attaching the greedy policy to each of these functions. So we'll kind of alternate between functions and their associated policies quite often. Right, so, and then, okay, basically what function class I used, like I was saying, we'll just pick that one that, for instance, we know from learning theory generalizes well. So we'll pick something with small VC dimension, small Rademacher complexity, maybe just finite, so that we know, we can finite things we can evaluate easily enough. And then maybe we are in good shape. So there is kind of a very natural candidate solution sketch you can design in the function approximation setting, which is you start with some initial guess for q star. Now, like I said, I'll attach a policy to each of the candidate functions, right? So if I pick f1, f1 has its associated greedy policy pi of f1. So I'll just pick a few trajectories according to that policy. Now, maybe I can use all this data that I've collected to somehow obtain a better estimate for q star than f1 was. So let's call that f2. And then I'll repeat this process. I'll act according to f2, collect some more data, maybe I find an f3 that's even better, and so on. Right? So maybe I can iterate this process if I know how to do this step, right? How to improve upon my initial estimate. Okay, so that's where one kind of, yes?
So in this setting, q star, do we still have that h horizon?
Yes. So these trajectories are going to be length h always, like here.
Okay, so but does that depend on where I am when I perform the action on the state?
Does what depend?
Does the my future reward depend on how long I'm in this trajectory already?
So the trajectory is, I think you're asking a version of Yishai's question, which is basically, so yes, q star in general in a finite horizon MDP will depend at every step on where you are in the sequence. However, I'm making the, for now, simplifying assumption that I encounter distinct states at step 1, step 2, step 3, which sort of allows me to not do this. Okay? But yeah, that's important.
Yeah, when we say better estimates, right? Like, so there is you have q star, and suppose I have a function.
Sorry, you don't have q star, so.
I'm saying suppose that I choose a function that is like a really large constant, right? Each entry is away by the same constant c. Like the distance between q star and that function is really huge, right? That would still give me the optimal policy. Mm-hmm. Versus I might get a really close function.
Absolutely. Yes.
It might not give you the same policy. So when you say better estimate, like.
So I haven't told you how to do this step. So once I tell you, that will make more sense. But you're right. In general, there are many value functions that will all describe the same optimal policy. But if you actually define q star to be the thing that always predicts the optimal long-term reward, then this sort of translation invariance goes away, because at the end of the day, like think about that maze again. Okay, so at the step where you've reached your goal, you know your reward is going to be 1. It cannot be 1 plus c. It cannot be 1 plus 2c. It is exactly 1. So that basically then constrains the value you can take. Right, and then you're just propagating back from there. Then you're just doing dynamic programming. So the way we formally define q star does not have this sort of.
I'm not talking about q star. I'm saying if you have a class of functions, then you are comparing two candidates functions.
Yeah. So I haven't told you how to compare them yet, right? So we'll come to that. Okay. So this is kind of the last sort of. Classical definition that I need to introduce before I can start talking about what we do. And that's our Bellman equation, right? And Bellman equation is basically a self-consistency check. So let's say I claim that I have found Q star, but you don't trust me and you would like to check my claim. Okay, so here's a very simple thing you can do. Again, let's think about this shortest path situation. So you ask me, I'm standing here. Okay, what's the length of the shortest path to the door? Fine. In fact, you ask me, if I were to take one step to the right, what's the shortest path to the door? And then I do take one step to the right, and you ask me, okay, what's the length to the shortest path what's the length of the shortest path to the door now? Now, if I'm not lying, my answer should be off by 1. And if I move one step to the left, my answer should increase by 1. If I move one step to the right, my answer should decrease by 1. So there are basically these consistency checks that you know Q star has to satisfy. And these consistency checks in reinforcement learning, they're called Bellman equations. So basically what they formally say is that, well, you're in you have a state action pair, you make a prediction, then you cancel off the instantaneous reward. What remains is what you would say at the next step. That's the high level idea. And if you're the Q star function, then you have to satisfy this equation at every state, at every distribution over states. So for instance, one thing I could do is I could act according to a policy for a while. I could take a policy pi, I could act according to it for 5 steps. I reach some distribution over states. I could evaluate the Bellman equation there on a candidate f. If it's Q star, it better be 0. I could pick a different policy pi, I could do the same thing. So, that's the high level idea, that there's a system of equations that Q star satisfies, which at least gives me one-sided certificate for something being Q star. Isha?
Because the way we model things, it's not really equations even, right? Because X can, right? Usually, like, you can reach a state in more than one way. In your formulation, a state is a certain. Basically, you start with the state which are distance h, and then you unfold it back immediately. Right? You cannot. There is only one way of reaching a state in your formulation.
No, because at level h, I might hit that state in several nodes.
Right. But when you go one step back, so essentially, sort of now, really, this Bellman equation sort of degenerates to just saying that when I'm in a certain state and I'm doing an action, I have a distribution of the next state. Their reward is already computed because things that happened before do not influence them, and then I just average it. It's just averaging from the leaves to the root, right? Unlike usually Bellman equations is equations, but here you don't need to solve the equation.
So that's true, that if you knew the values at all the states at the bottommost level, then you can definitely propagate them back. And I understand you're saying they're not equations because the variables here and the variables there are different. Okay, I agree. For now, I hope you'll let me call it a Bellman equation nonetheless. Okay, so here's a kind of fleshing out the earlier solution scheme a little bit more. In particular, judging the fitness of a candidate value function. Well, what I can do is, for given candidate value function, I can just check its, actually, for the most part, I'll not talk about Bellman equations, but Bellman errors. So that kind of avoids Yishai's question a little bit. So I'll check whether it has a non-zero Bellman error or not. Right, and if it has a non-zero Bellman error, I know it's not Q star, I'll discard it. Now, one thing that becomes a little bit cumbersome, so if I have a small number of states, I can check the errors in every state, and that gives me everything. But when I have a large number of states, checking all the Bellman errors becomes kind of difficult. So maybe I want to think about checking Bellman errors under various policies that I can act according to. But again, all possible policies are very large in number. So maybe I'll restrict myself just to the policies that are induced by functions in the class f. Right?
Just a technical question. The error epsilon is a function of f is a policy?
So f is a value function.
F is the value function, pi
Pi is the roll-in policy.
and h.
H is the number of steps you do the roll-in, right? So you take h steps according to pi. That has a certain distribution it's inducing over states, and then you evaluate the error. Yes.
I'm done.
Okay, and we'll call this validity condition. So if for some function f, you found that it has 0 Bellman error under all policies of this form, so all greedy policies induced by my function approximators, I'll call that a valid function. Remember, validity is now, so I've relaxed the definition quite a bit. This is not a certificate for being Q star anymore. This is a necessary but not a sufficient condition. You can have, in fact, really bad, you can have an F that induces a really bad policy, but is still valid, right? There's a very, there is various bad cases you can construct.
Is it like this that f is a value function of pi?
No.
Okay.
It can still be enormous, right? It can still be enormous.
Yes, absolutely. So, like Amma is pointing out, I mean, if I have, a large function class f here, I have a large number of policies here. Well, how do I check the Bellman error given a roll-in policy? I do a roll-in according to that policy. I evaluate the Bellman error. This means I have to collect some data under this policy, and if I wanted to basically compute this quantity for every policy corresponding to of this form, then I would have to actually collect naively number of samples that is linear in the size of this class. And therein lies the rub. So the problem is that you have all of these different policies. Naively, you have no reason to expect that data that you collect using one policy will help you in evaluating the Bellman error with respect to any other policy. They might all just reach different data distributions, different state distributions that are completely disjoint. And so somehow it just seems like an intractable problem so far, and that's kind of hinting at the fact that it's good that we are doing, it's maybe useful that we are doing function approximation, maybe it allows us to do some generalization, but it's not capturing the full story yet about how to do efficient learning. But nevertheless, it does give us some hint about what might allow us to do efficient learning, right? So the basic quantity we are looking at, these Bellman errors, what we can do is we can form a really giant matrix which has functions on both its rows and columns. Okay, so along the rows, we interpret f as a value function. Along the column, we interpret g as basically specifying a roll-in policy. And then the value of the matrix, the value of the entry, is the Bellman error when I use this roll-in policy for 8 steps to evaluate f. And I'll have one such matrix at every level. So I'll have the matrix at for h equals 1, for 2, and so on, right? So the trouble, once again, so I know that there is a row of all zeros in this matrix that corresponds to the Q star function. However, the trouble is that evaluating all the entries in even one row might be very expensive in general. However, we know a lot about putting structures on matrices. We know that, for instance, if matrices are low rank, then we can use a subset of knowledge about a subset of their entries to basically recover, to propagate information to a lot of other entries. And maybe that's useful. So that's what we'll do. We'll assume for now that this matrix is low rank, and the rank of this matrix will be called the Bellman rank. And one thing that's kind of very easy to see is that the rank of this matrix can be never larger than the number of states in an MDP, right? Because I know that if I know sort of the Bellman error in every single state, then I know the Bellman error under every distribution over states, and hence for every policy. So the number of states is kind of a direct and easy upper bound on the rank of this matrix, and that kind of tells us that, okay, I mean, at least this measure of complexity is going to be small for all of the small state MDP settings. However, there are other interesting cases. So for instance, if the transition matrix, remember, so we have we are in a state, we take an action, we have a next state, right? If I know that the transition matrix of this MDP has a low rank, that actually provides another upper bound on the rank of this matrix. And this is a more interesting upper bound. I could see states. I knew I could count how many they are. So that was kind of an upper bound I could measure. But now I don't know the transition matrix when I start out. I don't know what its rank is. So this is now we are getting to a more latent measure of complexity that I don't perceive. Right? You can actually kind of extend it when we go to POMDP-like settings, which I'm kind of skipping over for the most part. You can show that the Bellman rank is going to be bounded by the number of hidden states, in fact, at least when you're looking at basically only reactive value functions, so that don't actually reason over histories. Similarly, for PSRs, it's going to be bounded by the linear rank of the PSR and so on. So basically, what gets interesting about this Bellman rank is that it can be bounded in terms of various kind of structural and intrinsic parameters of the process that you don't necessarily get to observe, but that govern the hardness of the problem.
But you have a vector of ranks, right? For each H, you get a different rank.
Yes, for each H, I get a different rank. So we'll assume that they are uniformly upper bounded by some constant. Yeah. So for every H, they are upper bounded by some constant. Okay, now one way, Jeff?
Sorry, maybe you're going to say this, but continuous state spaces and continuous function classes?
Yeah, so continuous function classes is easy. Continuous state spaces, we studied a very specific example, which was LQRs. There we were able to argue that the Bellman rank is, I think, d squared if the states are d-dimensional continuous vectors. We haven't studied other continuous state settings, but it's quite plausible that we should be able to obtain some bounds even there. Our algorithm does not directly apply to continuous actions. So continuous states, I mean, for most part, I'm not really assuming that the states are discrete here. Like, states are always being drawn from distributions. The distributions might be continuous or discrete in any arbitrary way. Yes?
Are there finite number of value functions
in this, yes, but I'll mention at the end. Everything works for things that are qualitatively similar to VC classes. I'll be more precise. Other questions?
So, question, did you try to compute this rank or?
Yes, so we have a litany of examples, like I was saying, for instance, for all of the MDPs, we know it's bounded by states or rank of transition matrix, or for all of POMDPs, it's
like neural net one.
So no, empirically we haven't.
I guess you want the rank to be polynomial in some natural polynomial.
So yeah, yes. So your sample complexity is going to be polynomial in the rank, and that kind of gives you an idea that okay, you want the rank to be something that you can hope to allow the data to scale with. It's
like logarithmic in the observation space or something like that?
well, or like not too large depending on the dimensionality of the observation space, for instance, not necessarily in terms of the cardinality itself, but yeah, so something like that would definitely be at least my intuition. Yeah. But I think often it can actually be smaller, right? So one way, at least I think about this is kind of it allows you to think about both the different views of, for instance, this world at the same time. Like if it's the case that you're perceiving the world like this, but actually this is a pretty good model for your transitions, then the number of cells in this grid will be actually a good upper bound on the Bellman rank. And again, sort of, I'll describe how we sort of let a lot of things hold approximately. So the measures are actually pretty robust. Like the rank doesn't have to be an exact rank. It can be an approximate low rank factorization and so on. Okay. Sorry? Correct. Okay. So far, right? We've talked about basically trying to use function approximation for generalization. And we have this validity criterion, and we want to find a valid value function, and amongst basically all possible valid value functions in particular, we would like to find one that results in a good policy that leads to high reward. And now we want to design an algorithm that can do this. And the basic intuition we want to keep in mind is that Bellman rank is telling you that there is some underlying structure to your process which might aid the exploration problem, which might allow you to transfer information across the data that you're collecting. However, again, this is not explicit. You don't observe this. And it is not something you could do, for instance, at least not to my knowledge, by trying to measure a few entries of sort of the Bellman error matrix and then doing some factorization to actually explicitly construct this basis. I don't think that sort of an approach will work here. At least we thought about it a little bit, and it does not. Right. So that's so you're just so far you have this existence of a basis, and now we want to think about how to exploit it algorithmically. So so this is our algorithm. It's an iterative algorithm, and it kind of combines two very standard ideas in reinforcement learning. One is, as we've been talking about, the idea of using basically these Bellman errors, and the other is a very classical idea again of optimism in the face of uncertainty, and we'll see how the two interplay nicely to give an efficient algorithm, sample efficient. So we start with, so basically we'll start with the value function class, and we'll keep on refining it to throw out bad functions iteratively. So we start with the entire class. Now at each iteration, I first do this initial computation. Just think about for now that I can compute all the expectations exactly. That will help you understand things much better, and we'll talk about sample efficiency in a moment. Okay, so what I do is I measure how much value each function promises in the start state, in the distribution of our start states, right? So I check, I ask all of the value functions to report this number, and then I pick the one with the who's promising me the largest value, because that's possibly the best thing I can get, right? So I pick this function. This is my optimistic belief. But this function might be lying, it might be invalid, and hence it might not actually give me this much value, so I better verify their claim. How do I verify? I basically take its greedy policy, I collect a few trajectories according to it. What I know again is if this function was Q star, then if I actually acted according to it, I will get exactly the number it had promised me here. So if I get something close to what I was promised, I'm happy. I was promised a high number, I got a high number, I can go home. If I got a significantly lower number, then two things. I know this function is not Q star, so I should immediately throw this out of my function class. But actually I've collected some data using this policy, so I can do something more, right? I can evaluate basically a whole column of this Bellman error matrix using this policy, and I can throw out everything that has a non-zero entry in that column, because I know that Q star would have had a 0 entry in every column, right? So I can basically eliminate f, this ft function, but I can also potentially eliminate a lot more. Of course, maybe I won't, so I have to prove to you that I can. But I throw out a bunch of things. I refine my function class to a much smaller size potentially now. And then I repeat this whole process, and every step I do this optimistic computation only over the remaining functions. So that's the entire algorithm. First, let me tell you what the algorithm does. So let's still stay in the simple setting where Q star actually lies in my function class. Let's say the Bellman rank for all the H matrices is at most m, uniformly upper bounded. Then basically I'll give you a epsilon suboptimal policy using a number of trajectories that's basically at most this. So we have quadratic dependence on Bellman rank. We have some not too bad dependence on H and A. We have only logarithmic dependence on the size of the function class that you're using, so you can probably use a fairly big one. And 1 over epsilon squared is kind of unavoidable anyways. So So that's the main result for the algorithm. We can think about how this result maps back to some of the things we know or special cases we've been discussing. So the first thing it tells you is that because Bellman rank is bounded by a number of states in MDPs, it kind of recovers the fact that you can learn small state MDPs in a sample efficient manner. Actually, we know how to learn them more sample efficiently than our upper bound, but yeah, at least we are consistent with that case. However, now we can actually approach all of these other cases that we did not have sample efficient algorithms in before, and also learn them efficiently, where now the sample complexity will depend on these underlying parameters like the rank of the transition matrix or hidden states and so on. Right, so in that sense, it's sort of a nice unifying treatment for doing sample efficient reinforcement learning in many, many different models that people have thought about.
Efficient in a parameter that we don't know anything about, we know very little about.
Sorry?
It's efficient. Efficient in a parameter that we know very little about. I mean,
well, I mean, so
I can define efficiency in the parameter, which is the optimal, which is kind of the number of explorations that I have to do, and then I will always be efficient.
Certainly. So as long as it's a parameter that we can define and we can show that it is reasonable in a bunch of settings that we care about, I think that's kind of an interesting thing. Now, maybe what you're asking is if I can also prove an analogous lower bound, for instance, that this is really the most intrinsic parameter, and I think that would be actually interesting. We don't have such a result yet. But yeah, you're absolutely right. This is a parameter we defined, and the best justification we have is that it's reasonable in many settings. Yishai.
So one does show up in many cases in MDP, in POMDP, so in POMDP like a multiplicity automata.
Yeah.
They are defining like a very similar
right.
matrix. Can you relate the different
so
notions from the 50s and 60s to your notion?
Yeah, we were looking at multiplicity automata literature, and I'm now blanking on the exact connection that. So I think the bottom line is that you. Okay, I'm just totally forgetting, but we looked at that, and you could not, as far as I remember, you could not immediately get this sort of a result out of sort of mapping the setting.
Asking whether those lengths are related.
So yes, so actually right. So I'll answer by special case, right? So for instance, let's look at just PSRs.
Okay.
So in PSRs, the Bellman rank is bounded by the linear rank of the PSR. So yes, there's definitely a connection. But for instance, for PSRs, we did not have a result saying, okay, the amount of exploration you have to do depends on the linear rank of PSR, which we do now. Yes, you have a remark?
I think in general, our Bellman rank depends on the function approximator.
Yes.
Most of this work does
That's
not
true.
include a function approximator at all.
Okay.
So it's somehow a slightly different definition.
Yeah.
Suppose if all the rewards were the same, right? Then there is the rank is 0 or something?
If all the rewards were the same, then the Bellman error for every function will be 0, right? So you'll just, everything is valid and...
Rank 1.
Yeah, exactly. I mean, then it's just going to be a 0 matrix, so you're fine. Jeff?
So why is it assuming Q star, or why is assuming Q star is in F? Why is that not a strong assumption?
Yes, so it is.
I guess, I mean, have you considered agnostic variance?
Give me 2 minutes. I will come to it.
Okay.
I'll give you a weaker result that we can prove in the agnostic setting. It'd be great if we can make it stronger. I don't know how to. Okay, so I just want to very quickly highlight a couple of properties. So the correctness of this algorithm is kind of immediate by construction, right? So I can prove very easily that Q star is always retained by the algorithm because it always has 0 Bellman error. Now at every step, I find a function that's promising the highest value. So it is promising a higher value than Q star. And if it actually gives me that value, then I've basically found Q star. So when I terminate, I've definitely found the right thing. So I have to just to prove to you that I can terminate in a small number of iterations, and that's where the Bellman rank basically comes in. So what you can think about this, like all of the Bellman errors that you have, they are linear. They basically describe some linear equations, and every time you basically measure the Bellman error under some new policy and throw out the functions that have non-zero Bellman error and look at the matrix corresponding to the residual functions, you can prove that its rank will be strictly smaller by 1 if you are computing all the matrices exactly and doing elimination exactly at 0. So in sort of the noise-free case or infinite sample case, this is just a very algebraic argument that you have a matrix of rank m. At each step you reduce its rank by at most 1. You have one such matrix for each level, so you have to m times h total iterations that you would need to execute, which will just terminate the entire learning process. Now, you have to make all of this reasoning robust to noise because the computations are happening with averages and not expectations. Turns out because we are working with linear equations, you can kind of like do a geometric argument. You can construct some ellipsoid and show that its volume is sort of reducing by a constant amount at every step, and that allows you to basically show that up to log factors the algebraic argument was basically correct. So that's the high level idea that tells you why. And then because we can bound the number of samples we collect just by standard sort of at every step you're doing something much more standard learning wise, like you're basically doing maybe some sort of a regression problem almost. So you can control the number of samples you gather at every step, and so that kind of gives you the overall sample efficiency. Yeah.
Okay, I can see that if you compute everything exactly, then you can eliminate the column.
Mm-hmm.
But why isn't the variance increasing for things which are very different than you? So for policies which sort of have a non-zero entry, but they're in this matrix, but they're very different than your policy.
Yeah. So
I'm thinking like important sampling. So why isn't the variance increasing?
So what's sort of happening is
This is fun.
You discard. Okay, so you accept it unless you know that basically this means that the Bellman error.
No, the reject part. If you
yes.
go down this line,
yes.
this is the line I'm worried about. Why isn't the variance in estimating the entries of other policies is not?
So the way formally the way we do this is So you'll take eight steps according to pi t, and then you'll take the next action basically uniformly at random, and then you can construct just like by importance sampling, like you were saying, estimates for every function. So, but this is a factor of k. We are assuming finite number of actions, right? So this is just a factor of number of actions that we can control. I can gather basically samples that are a times more. So yeah, maybe I'm suboptimal in my dependence there a little bit, right? But this is something I can control by gathering a little bit more data. I mean, think about the fact that this is the true expectation, and okay, I'm gonna approximate this expectation to some accuracy new, and then we can think about, okay, what is the new that makes the theory work, and how much data do I need to satisfy that new, and we can do that. So that's what allows you to circumvent that, the fact that the data is not really exponential in anything and not a very large polynomial in anything that you need to satisfy this thing approximately. Okay, so I think I have massively shot over time. So I'll just quickly mention a couple of things. So Jeff asked me about what happens when I'm in an agnostic setting. I can tell you that I will find a valid value function that has the best policy. I can find you an approximately valid value function that has the best policy. But if you go to completely invalid, so things that have just ridiculously large Bellman errors, but somehow induce good policies, I cannot find them. I don't know how to find them. Okay, but we can sort of give you a meaningful characterization of the quantity that is returned by the algorithm when Q star is not in the function class. Maybe that's sometimes interesting or not.
We can clarify. You're not guaranteeing that the thing you find. You're not guaranteeing anything in your big F is bad.
like that.
Yeah, so that's good. So that's something I didn't say, that implicitly the assumption I'm making is that we have at least a valid value function, which is kind of a weaker version of realizability, that Q star lies in F. Right, I can allow basically F to have F to be infinite. I kind of need the value functions to have a small pseudo dimension and the induced policies to have a small Natarajan dimension, because this is sort of a multi-class type setting. So as long as sort of those two things are fine, I can show that all of the reasoning goes through. We can allow errors in, so the low rank factorization in low rank does not have to be exact, it can be approximate. All of these things work. So basically, quickly wrapping up, the high level idea is that we have this new notion that's trying to characterize when can we do efficient exploration in reinforcement learning. There are caveats, like Shai was pointing out. But I think the interesting thing we derive out of it is that we do get sample complexity results in many reinforcement learning models where we did not have them before. And I think we show in the paper in a fair bit of detail that the algorithm is pretty robust to various modeling assumptions. I think the main thing that sort of dissatisfactory so far is that this is an elimination-based algorithm. So I'm implicitly sort of enumerating over the function class, which means I don't know how to implement it. And I think that would be great to figure out. That would be very useful. And yeah, happy to answer any further questions. Andre.
Can you comment on how these results relate to what's known as the contextual bandits, right? I mean,
yeah, so contextual bandits is a special case where the Bellman rank is 1. So they have a suboptimal dependence on number of actions in comparison. It should be linear, and so both M and H are 1 in contextual bandits, but this should be A instead of A squared. And I think that would be good to figure out, but currently, I mean, I know where we lose it, but I don't know how to fix that so far. So yeah, I think definitely, like sample complexity wise, I think there are suboptimal exponents on basically everything here. So except epsilon, right? So, yeah. So I think improving them would be quite nice. But I think in my mind, kind of the computational question takes precedence. So that's the one I'm thinking about much more at the moment. Yes?
That would be the next one, right? Is there sort of any special cases, at least, where this is efficient?
Unfortunately, I can't even make it efficient in tabular settings, so no. Emma?
We know sometimes in practice that optimism is overkill. Do you have any ideas of how these similarities can be applied to like Thompson sampling algorithms, or is there any way we could maybe?
Yeah, that's a good question. So I think what will happen is for the hypothetical computationally efficient algorithm that we will get, it will be doing not quite exact maximization, but it might do, it might basically operate by inducing more something like a distribution over these policies that is sort of approximately optimal, but not quite, and that would probably structurally look similar to Thompson sampling type thing. But I cannot make an explicit comment about whether like something closer to Thompson sampling would just directly apply or not. I don't know.
Great, let's thank our speaker. Now we have lunch until 1:30. We'll start back with the afternoon session.